Hello everyone. Today we will look into the technical report of StepVideo-T2V. This is a newly dropped open source, open weights video generation model from an AI company called StepFun from China. The technical report contains an incredible amount of details on how the model is trained, similar to how DeepSeek does it with their technical reports with high level of openness. The model has 30 billion parameters and is capable of generating videos up to 204 frames. Here you can see some example videos generated. Looking at the per frame quality, temporal consistency, and fidelity of the details, they are quite impressive. The main components are video VAE for compression to latent space, bilingual text encoders, and 3D full attention diffusion transformer, the flow matching training, and video DPO alignment with human preferences, plus some system level optimizations. Let's dive in. Videos contain enormous data. To reduce complexity, StepVideo-T2V uses a video VAE that compresses the spatial dimension 16 times 16 and the temporal dimension 8 times. The dual path encoder has a conv path and a shortcut path. In conv path, causal 3D convolutions are applied so that each frame depends only on previous frame and uses pixel unshuffling for coarse downsampling. The shortcut path does group channel averaging to preserve structural semantics. The two paths are fused to blend high-frequency detail with robust low-frequency features. The decoder is symmetric to encoder, with pixel shuffle operations and residual blocks to reconstruct video frames. They train it in stages, first at a lower compression ratio, then unfreezing deeper layers. Losses include L1, video, LPIPS, KL, and a gang objective to balance sharpness and realism. Next, StepVideo-T2V processes user prompts with two bilingual encoders. One is short but strongly aligned with the visual space. The other can handle very long and complex text inputs. By concatenating their outputs, the model supports variant length prompt in both Chinese and English. The heart of StepVideo-T2V is a large diffusion transformer that uses 3D full attention. Rather than splitting temporal versus spatial, it unifies both dimensions in each attention layer. Although more expensive, it better captures spatio-temporal correlations. Cross-attention injects text embeddings from two bilingual encoders between self-attention and feed-forward layers. Adaptive layer normalization is a simplified single version for lower overhead. Rope 3D extends rotary embeddings in 3D for time, height, and width. QK norm normalizes query key dot products to stabilize large-scale attention training. The model uses flow matching as the training objective for the video generation. The core idea is to train the network to predict a time-variant velocity field that connects noise and data. At inference time, we can map a noise into a sample using the learned velocity field. It has become a standard in video and audio generation models. Rectified flow refines this idea by placing extra emphasis on the time endpoints, allowing the model to take larger leaps in its ODE path. Practically, this means fewer inference steps are required to go from pure noise to a high-fidelity video latent, particularly useful for long videos. The authors created a turbo version of the model through self-distillation with a rectified flows objective and a specifically designed inference strategy. In this approach, a two-rectified flow model is trained to mimic the base model's predictions, but with more aggressive time-step scheduling, the so-called U-shaped distribution. We also gradually reduce the classifier free guidance factor during inference. The result is a model that maintains near equivalent video quality but drastically cuts the number of function evaluations, making text-to-video generation much faster in practical settings. To refine the final video style and correctness, the model uses direct preference optimization. Multiple video samples are generated for each prompt. Human annotators pick preferred versus non-preferred videos. The model is updated to favor preferred samples. A reference model ensures it does not diverge excessively. A reward model is sometimes trained in parallel to score new samples on the fly, improving data efficiency. This technique aligns outputs with human preference and reduces artifacts or distortions. Now, Before we can talk about the training strategy, we need to look at the data first. The team begins by collecting 2 billion video text pairs plus 3.8 billion image text pairs. Then perform the following steps. Segmentation. Long videos are split into single shot clips using scene detection, trimming transitional frames to avoid flicker or abrupt camera changes. Captioning. An internal vision language model generates short and dense captions so that each clip has textual labels beyond the original metadata. Quality assessment. Each clip is scored for aesthetics not safe for work content, watermarks, subtitles, saturation, blur, and black borders. Only clips passing certain thresholds survive. Motion analysis. Measure average or maximum motion using optical flow to ensure variety in dynamic content. Concept balancing. Clips are clustered by visual embeddings to maintain coverage across concepts and remove outlier clusters with scarce or repetitive content. Alignment check. A clip score step filters out pairs that are poorly matched to their text descriptions. This pipeline progressively shrinks and refines the dataset. After all these filters, we obtain a curated pool suitable for training and building the final high-resolution model. Finally, let's look at the full training pipeline. First stage. Text-to-image pre-training acquires foundational spatial understanding from 3.8 billion image text pairs. Second stage. Text-to-video and image pre-training is mixed training at lower resolution, first to master motion, then move to higher resolution. Third stage. Video fine-tuning is strictly on text-video data to improve style consistency. Fourth stage. Direct preference optimization is the final alignment with human preferences. In particular, the authors progressively filter the data to create 6 pre-training subsets for Step 2, text-to-video and image pre-training. During the pre-training, the sudden loss reduction is highly correlated with the quality improvement of the training data. In the technical report, the engineering practice for system-level optimizations, including key aspects of parallelism and simulation, communication, load balancing, and monitoring, are also described. Human evaluation confirms strong performance with 4 evaluation criteria: instruction following, motion smoothness, physical plausibility, and aesthetic appeal. StepVideo-T2V often outperforms or ties top open source and commercial models, excelling at complex motion and extended clips. The authors also mentioned some of the challenges facing today. High-quality labeled data is difficult and expensive to obtain. Instruction following require a lot of attention to details, and the ability to adhere to laws of physics has a lot to improve. Lastly, it's worth mentioning that the paper envisioned 2 levels to describe how advanced a video foundation model is. The level 1 is translational. These models are great at translating text into video, but less capable of deep causal reasoning. The big names that we are familiar with, including the step video in this paper, are currently at this level. Future improvements might nudge them towards level 2, where they'd simulate real-world physics or multi-step events more reliably, similar to how large language models can perform causal reasoning, but in video form. I believe the community can benefit a lot from this work, and I hope StepVideo's open release can promote further breakthroughs in video foundation modeling. That's it for today. Thank you, and see you in next video.